We're going to find the surface area of the part of the cone z equals square root of x squared plus y squared. So that's the upper part of the cone, right? It's not the full cone. That lies between the plane z equals 1 and z equals 4. So I'm not going to attempt to draw this whole picture, but I can draw a little bit of it. So you have a cone. The upper part of the cone, where's the vertex of this cone going to be? Yeah, at the origin, yeah, 0, 0, 0. So there's the origin right there. I'm not drawing the axes, but I do know z equals 1. It looks. What does that look like? What does that look like? Horizontal plane, height 1, right? So when it cuts it, it's going to create, well, a circular cross section, right? So maybe that's at a height of 1, right? And then z equals 4. So we'll say that's at z equals 1, right? So it cuts it, and inside it creates a little disk. Not that we're going to integrate over that or anything. Z equals 4 might be up here. It'll create another bigger circle, right? Circular cross section anyway. And so that's the part of the plane we're interested in, right? The part that cuts through the upper part of the cone. But really what we're going to do is find the lateral surface area then of that cone, right? So it's important to understand what it is we're finding. We're finding this lateral surface area, aren't we? Does everybody see that? Yeah? So the surface area formula, first of all, I'll just call it area, I guess, is really equal to the double integral. What's our area element? If we call this guy f, what's our area element? Square root of something times dA, right? So 1 plus the partial with respect to x squared, partial of f with respect to x squared, plus partial of y, partial of f with respect to y squared. Would you buy that so far? Over some region R, we still have yet to determine what that would be. So I think the problem that all of you are going to have is what the heck is R? Okay, I mean, I think you can find the partials with respect to x and y if this guy is z, right? I don't think that's going to be a huge issue. Well, remember, we kind of treat it like, well, not kind of, we treat it exactly like how we set up double integrals back in chapter 15, except we have, of course, this special integrand here. So think about it. What object do we get in the xy plane if we project this down? Now, I guess there is one difference. We thought of it as a solid that we were projecting down into the xy plane back in chapter 15. Here, we're really just thinking of projecting the surface area down, right? So so imagine projecting this down. You know, imagine projecting this whole edge of this disk down. If that's all we were projecting down, then we'd get a big old disk, wouldn't we? In the xy plane, right? But we're also projecting this edge down, aren't we? And so we're not going to count the part in the middle. This is the hole, right? We're not counting that part. Really what we're looking at then is it, well, it looks like a donut or a tire, right? So that region, so let me do a 2D picture then for you. So here's the xy plane, and okay, this inner disk or circle, however you want to look at it, what's the radius of that thing? That's when z equals 1. So that corresponds, if you square both sides, to 1 equals x squared plus y squared, right? So circle radius 1. Okay, so that inner disk I'll do is circle radius 1. What about this outer disk? What's the radius on that? It's got to be 4, right? Because you plug 4 in here. But when you put in standard form, you square both sides, and you get x squared plus y squared equals 16. So let's say we go out to 4. Let's say that distance is 4. I'm going to cheat on it a little bit so I don't have to draw such a large circle. Okay. Let's say that distance is 4. Then in 2 dimensions, your region of integration is going to look like that. To me, that's the hard part on this problem. If you don't have a lot of experience, you might not have come up with that. It's called an annulus, is what it's. But I think of it as a donut because I used to like donuts anyway. Tire, right? So, all right. So now I think we're in business here. Remember, this radius, this is out a distance of 4 right here. This is out a distance of 1 right there. Okay, let's go ahead and find the partial with respect to x. So what's that going to be? 1/2. Get you started. 1/2.
1/2 times x over the square root of x squared plus y squared.
X squared plus y squared to the negative 1/2?
Negative 1/2.
And then times
2x.
that's supposed to be a dot for times 2x. Okay, and then of course that simplifies the 2's cancel to what you were about to say, right? Square root 2 divided, or I'm sorry, should be x on top, divided by the square root of x squared plus y squared. And then I think if we think in parallel here, it's going to just be for the partial with respect to y on top, divided by the square root of x squared plus y squared. Everybody agree with that? Okay, and so this thing, now this is a good time to remind you, when I include the square root with the dA, that's what we think of as ds, right? An infinitesimally small patch of area on this surface in green right here. So let's write that down. So what would that look like? And I bet it simplifies nicely here. So it would be we have to take this guy, square it, take this guy, square it, add 1 to it, and then take the square root of the whole thing. So so I'll put the 1 first, and then what does this guy become when you square it? X squared over x squared. Do you guys see what's going to happen here? It's really nice.
Yes.
Plus y. That means a teacher who cares wrote this problem, that's going to cancel so nicely. Yeah. X squared plus y squared. And then of course we do have the dA out here. Does everybody see why it's so nice? Because when you have the common denominator here and here, and so you're going to add those two fractions together, get x squared plus y squared over x squared plus y squared. That's 1, right? Mm-hmm. Add it to the other one. Excuse me, sorry. And you get root 2 dA. Well, that's nice. I mean, it's artificial, right? But it's artificial so you can do it by hand. Otherwise, you'd have to use machines for a lot of these integrals, or estimates for a lot of these integrals. So, all right, let me get some screen real estate here. Can you still see all that? Yeah. All right. So then my area integral becomes just filling in this formula. The double integral. I'm still going to call it R. And then square root of 2 dA, which is going to equal, I'll start up here. What are we going to want to switch to? Good old polar coordinates. So you see this tire-looking region. You can draw in to get the limits on your R, draw in a spoke, a representative spoke. Now the spoke's actually, this part's not part of it. I tried to make it dotted, it didn't work. So you want to make it radial from the origin, but really it's the part that goes over part of the donut, not from the origin, right? So let's throw in the r d theta. And The square root of 2 still is just square root of 2. So let me write that out front, I guess. So I pulled this guy out front, and then the limits of integration on r go from what to what? 1 to 4. And then what does theta go? From 0 to 2 pi. And that's not so bad, right? You guys want to take it from there? Do you want to see me do this one? Okay. So we'll let you take it from there. So if you evaluate that, hopefully you get 15 pi times root 2. That's what I have as my answer here anyway. Okay? So that would be surface area. So what, if you were given units, linear units of feet, what would the units of the answer be in? Like square feet, yeah.